I am interested in knowing about, I have a random variable x, I have defined expectation of a random variable x. Now, suppose I am interested in knowing about expectation of say x square or expectation of 3x or expectation of 3x square. So, I am in other words, we are interested in knowing about expectation of a function of x. So, if I have x which is a random variable which again takes, for now I am assuming it takes finite number of values, then g of x is going to take g of x1, g of x2 with values g of xn. The probabilities would remain the same. So, I have probability x equal to xi is probability x equal to x1, probability x equal to x2 up to probability x equal to xn. I know expectation of x is going to be x1 probability x equal to x1 plus x2 probability x equal to x2 plus xn probability x equal to xn. I can define expectation of g of x to be g of x1 into probability of x equal to x1 plus g of x2, because it takes value g of x1 with probability x equal to x1, it takes the value g of x2 with probability x equal to x2, it takes the value g of xn with probability x equal to xn, and that is what is summarized here as expected value of g of x is summation over all values of x g of xi into probability x equal to xi. As a natural corollary for it, if g of x, so suppose I have now g of x is a constant times x. Suppose g of x is just a constant times x. Okay, g of x is a constant time x, then I know that again let x take the value x1, x2, xn. G of x is going to be ax1, ax2, axn. Expectation of g of x is going to be ax1 into probability x equal to x1 plus ax2 into probability x equal to x2 plus so forth xn into probability x equal to xn. I can remove a outside. I get x1 probability x equal to x1 plus x2 probability x equal to x2 so forth plus xn probability x equal to x. So, we can recognize this term inside the bracket is expectation of x. So, we can recognize that this value inside is expectation of x, hence I can write that expectation of a constant times x is nothing but a times expectation of x, a is a constant. So, similarly, let us look at the case where g of x is equal to ax plus b, where a and b are constants. So, again let us look at that case where I have both a and b are constants. So, what do I have? I have my x. So, I have my x which is taking the value x1, x2, xn. My g of x now is going to be ax1 plus b, ax2 plus b up to axn plus b with the same probabilities. This is probability x equal to x1, this is going to be probability x equal to x2, this is going to be probability x equal to xn. So, my expected g of x is going to be ax1 plus b into your probability x equal to x1 plus ax2 plus b into your probability x equal to x2 plus axn plus b into probability x equal to xn. Now, we can see that this is nothing but I can write this as a into x1 probability x equal to x1 plus x2 probability x equal to x2 plus xn probability x equal to xn, the first portion, and the second I can write it as b into probability x equal to x1 plus probability x equal to x2 plus probability x equal to xn. Now, the first portion, that is, this is nothing but expectation of x. Now, since I have the second portion, this is going to be a probability mass function. So, this adds up to 1. Hence, I can check and verify that expectation of ax plus b, where both a and b are constant, is the same as a expectation of x plus b. And this arises as a general corollary to expectation of g of x is the same as summation g of xi into probability x equal to xi. So, now let us look at a simple example where x is a discrete random variable with the following distribution. Again, is this a probability mass function? X takes the value minus 1, 0 and 1. Yes, this is a probability mass function because 0.2 plus 0.5 plus 0.3 equals to 1. So, it is a probability mass function. I have each probability greater or equal to 0. Now, let us define g of x. So, let y be another random variable which is equal to g of x, which is equal to x square. So, again x takes the value minus 1, 0, 1. G of x takes the value x square, which is going to be 1, 0, 1 with probability 0.2, 0.5 and 0.3. This is probability x equal to xi, the same probability. So, my expected value of g of x, which is my expectation of y, is going to be 1 into 0.2 plus 0 into 0.5 plus 1 into 0.3, which is equal to 0.5. So, I have expectation of g of x is 0.5. Now, when you notice g of x, I can also write this as y, which is g of x, takes two values and those values are 0 and 1. Now, what is the probability with which y takes the value 0? The probability with which y takes the value 0 is 0.5 and the probability with which y takes the value 1 is 0.2 plus 0.3, which is again a 0.5. Hence, if I look at from the first definition expectation of y, it is going to be 0 into 0.5 plus 1 into 0.5, which is equal to 0.5. This matches with what we got earlier. Hence, given a random variable, I can find out what is the expectation of the function of a random variable. A very common mistake people do is to think expectation of x square is the same as expectation of x whole square. What we have seen just now is expectation of x square was 0.5. What is expectation of x? Expectation of x is minus 0.2 plus 0.3, which is a 0.1. So, the x square of the expectation is 0.01. So, expectation of x square is not equal to expectation of x whole square, and this you should be very careful about understanding this, that expectation of square of a random variable is not the same as square of expectation. So, expectation of square is not same as square of expectation. The next example where we go for an application of what we have learned is the following application. So, Sanjay and Anita work for the same company. Anita's Diwali bonus is a random variable whose expected expected value is 15,000. So, let x be the random variable which represents Anita's bonus. What is given to me is expectation of x is 15,000 rupees. So, that is what is given to us. Now, the next thing that is given to us is Sanjay's bonus is equal to 90% of Anita's bonus. So, let y be Sanjay's bonus, x is Anita's bonus, y is Sanjay's bonus. What is given to us, y is 0.9 times x. I know what is expected x, this is given to be 15,000 rupees. So, the question is what is expected value of Sanjay's bonus, that is expectation of y. From our earlier result, I know that if y is 0.9x, then expected value of y is 0.9 times expected value of x, which is 0.9 times 15,000 rupees, which is 13,500 rupees. So, I can see that Sanjay's bonus, expected value of Sanjay's bonus is 13,500. But suppose Sanjay's bonus is said to be equal to 1,000 rupees more than that of Anita's bonus, then find the expected bonus. So, in this case I have y is x plus 1,000. So, expectation of y is going to be expected value of x plus 1,000. I already know expected x is 15,000. I add 1,000, hence the expected value of Sanjay's bonus is going to be 16,000 rupees. So, you can see how we have just applied the expectation property of expected value of Ax plus b equal to A into expectation of x plus b. In this case, my A was 0.9 and b was 0. In this case, A was 0 and b was 1,000. So, just you need to identify what are your constants to apply this property. Now, let us look at what can I tell about expectation of a sum of random variables. If I am given two random variables with and I know their relative or respective expectations, then expectation of x plus y, that is expectation of sum, is sum of expectations. We are not proving these, but let us look at example. Again, roll a dice. If I am rolling a dice and I say, okay, I roll one dice, I roll another dice, the sample space in both these experiments are going to remain the same because I am just rolling a dice. So, if x is denoting the outcome here, we have already seen expectation of x in this case is going to be, I have already seen this expectation was 7 by 2, which is 3 by 5. Again, if y is representing the outcome in rolling the second dice, I also know expectation of y is again 7 by 2. So, if x and y are outcomes of rolling dice separately, I know expectation of x is equal to the expectation of y, which is equal to 7 by 2. Now, what is x? X is the outcome of the first dice, y is the outcome of the second die. So, x plus y would denote the outcome or sum of outcomes of both the dice. Sum of outcomes of both the dice is equivalent to, so rolling a die twice. So, you can see that expectation of x plus y from my formula is expectation of x plus expectation of y, which is 7 by 2 plus 7 by 2, which is equal to 7, and this matches with our x plus y, which was same as the expectation or sum of outcomes of rolling a dice. So, now let us look at an example of another important random variable which arises in a lot of application, and this is referred to as a hypergeometric random variable. A hypergeometric random variable, suppose I have m of one type and I have n minus m of another type. I have total of n balls, I can, or n people, of which m are of one type and n minus m are of another type. Here I am assuming m are red balls and n minus m are blue balls. From this n, I am choosing a sample of size n. So, this is my sample of size n. Again, this sample also could have red balls and blue balls. The question we are interested in knowing is, suppose for example, I have 5 balls. Of these 5 balls, I have 3 red balls and I have 2 blue balls, and I am choosing from here 2 balls at random. Then the possible choices for these 2 balls is, I could have both are red, I could have one red and one blue, I could have both are blue balls. These are the possible chances I can have. So, if I look at the number of red balls in my sample, the number of red balls here are 2, number of red balls here is 1, the number of red balls here is 0. Okay. So, in this, if I am choosing both blue balls, I do not have any red ball. If I have one blue ball or one red ball, I have one red ball, and here I have 2. Similarly, if I am counting the number of blue balls, here it is a 0, here it is a 1, here it is a 2. So, the random variable of interest in this case could be the counting the number of red balls or blue balls. The probability mass function, for example, if I am looking at this example here, so here the probability mass function, where x is the number of red balls that are chosen, and I have said that this I can take value 0 to n. Again recall, I have n, I am choosing n. In this I have m red, I have n minus m blue. So, I could have both red balls, or I could have all the n red balls, or I could have all the n blue balls. So, I could have 0 red balls. The probability mass function or the probability distribution is given by this expression. How we get this expression would be discussed in tutorials, but this is the expression. And you can also verify that this expectation of x is n into m by n. A variable of this kind, a discrete variable of this kind which takes value 0, 1 to n, is referred to as a hypergeometric variable for values of n, m and capital N. Let us look at an application of the hypergeometric random variable. I am choosing 2 students from a group of 20 boys and 10 girls. So, my capital N is 30. I have 30 people. In these 30 people, I have 20 boys and 10 girls. So, this was my M. This is my N minus M, which is 30 minus 20. This is of one type, this is of another type. I am choosing small n, which is equal to 2. Okay, I am choosing 2 students. Again, it could be both girls, both boys, or one girl and one boy. So, my probability mass function of x equal to I will follow what I have here. M choose I, my M here is equal to 20. my capital N equal to 30 and my small n equal to 2. I can plug in these values in this equation of mine. What I am interested in knowing is the following. So, my expected value of x is going to be n into m by n, which is 2 into 20 by my 30, which is 4 by 3. So, you can see that the expected value of x, where I recognize n equal to 30, m equal to 20 and n equal to 2 is 4 by 3. Now, y is denoting the number of girls that is chosen. So, if y is the number of girls that is chosen, now everything else capital N remains 30, small n also remains 2, but my m is now going to be equal to 10 because I have only 10 girls. So, in this case my expected value of y is going to be m into n by n, which is 10 into 2 by 30, which is 2 by 3. That is my expectation of y can be shown to be equal to 2 by 3. Again, by assuming or by seeing that y is a hypergeometric variable with m equal to 10 and n equal to 2. Now, what is the expected value of x plus y? I can check that expected value of x plus y is expectation of x plus expectation of y, which is 4 by 3 plus 2 by 3, which is equal to 2, and I get expectation of x plus y is equal to 2. I can extend this property. What is the property? Expectation of sum is sum of expectation to more than 2 variables. In other words, if I have x1, x2, xk discrete random variables, then the expectation of the sum, which is equal to x1 plus x2 plus xk, is equal to expectation of x1 plus expectation of x2 up to expectation of xk. When k equal to 2, it would reduce to what we have discussed earlier. So, now let us look at the experiment of tossing a coin 3 times. We already know that if x is the number of heads, then we have seen that expectation of x is 3 by 2. This is what we have seen already. Now, let us look at this experiment. I toss a coin once, I toss a coin second, or toss one coin, toss two coin, toss third coin. Let x1 be the random variable which takes the value 0 for a tail and 1 for a head, with probability equal likely half and half. I know expectation of x1 is equal to 1 by 2. Similarly, let x2 be the random variable, again takes the value tail and head with the same probabilities. Expectation of x2 is again half. x3 again takes the value 0 and 1 with probability 1 by 2, 1 by 2. Expectation of x3 is again equal to half. Now, x1 plus x2 plus x3 is the same as total number of heads in 3 tosses or the 3 coins, which is same as number of heads when I toss a coin 3 times. I can verify that expectation of x1 plus x2 plus x3 is expectation of x1 plus expectation of x2 plus expectation of x3, which is half plus half plus half, which is 3 by 2, and this matches with what we already obtained for the expectation of number of heads when you toss a coin thrice, okay, which is 3 by 2. So, in summary, what we have introduced so far and what you should be knowing now is the notion of the expected value as a long run average. A word of caution is, do not interpret it to be that is the value the random variable will take. For example, we saw that x cannot take a value 3.5 when you roll a dice once, but rather it is the average of the outcomes. The formula to compute an expectation of a random variable, which is summation over all values of x, x into probability x equal to x. Expectation of a function of a random variable, which is summation over values of x, g of x into probability mass function, and expectation of the sum, which is the same as sum of expectations. And we looked at how to apply these concepts. So, the next thing which we are going to look at is what we mean by variance of a random variable. We are going to focus on the variance of a discrete random variable.